Hello everyone, welcome to this video where we'll dive into the fascinating world of large-scale data processing with PySpark. PySpark, the Python API for Apache Spark, is a game changer for handling massive datasets efficiently. Whether you're dealing with terabytes of data or processing complex pipelines, understanding how to optimize PySpark for large-scale processing is essential. In this video, we'll explore key strategies, techniques, and best practices to help you master large-scale data processing in PySpark, making your workflows faster, scalable, and more efficient. Introduction. Handling large-scale data processing in PySpark is all about harnessing Spark's distributed computing power to manage massive datasets efficiently. This involves optimizing resource usage, minimizing data movement, and fine-tuning your applications for performance. By leveraging techniques such as partitioning, caching, and using efficient file formats like Parquet, along with strategies like optimizing joins and managing shuffle operations, you can streamline your PySpark workflows to handle even the most complex data processing tasks with speed and scalability. Let's dive in. 1. Partitioning the data. Partitioning plays a crucial role in efficiently handling large-scale data processing in PySpark. It ensures that data is evenly distributed across the cluster, enabling parallelism and making full use of the available computational resources. By default, PySpark automatically determines the number of partitions based on factors like the input file size and the cluster configuration. This is known as default partitioning, and while it works well for many cases, it may not always be optimal for specific workloads. To gain finer control, PySpark offers two key methods: repartition and coalesce. The repartition method increases the number of partitions, which is particularly useful when you're dealing with a large dataset and need to improve parallelism. By creating more partitions, you allow Spark to distribute the workload across more nodes, thereby speeding up processing. On the other hand, the coalesce method reduces the number of partitions. This is especially helpful when the dataset size shrinks, such as after filtering operations, and you want to minimize resource usage by consolidating partitions and reducing the overhead of managing empty ones. By strategically using partitioning techniques, you can optimize Spark jobs, balance resource usage, and significantly improve the performance of your large-scale data processing tasks. Practical example. This PySpark example demonstrates the concept of partitioning, which is essential for distributed data processing. Let's break down the steps and understand the flow of this code. Step 1: Initializing the Spark session. The first step involves creating a Spark session, which serves as the entry point to interact with Spark. Using Spark session.builder, we initialize the session and assign it the application name partitioning example. The getOrCreate method either creates a new session or reuses an existing one. This session provides the environment needed to create and manage distributed datasets. Step 2: Default partitioning. Here we create a small dataset as a list of tuples, where each tuple contains a name and an age. Using created data frame, we convert this dataset into a Spark data frame with two columns, name and age. By default, Spark determines the number of partitions for this data frame based on the cluster's configuration, including the input file size and the number of available cores. To check the number of partitions, we call the getNumPartitions method on the data frame's RDD representation. For small data sets, Spark typically defaults to a single partition, but this can vary depending on your setup. Step 3: Repartitioning data. The next step demonstrates how to increase the number of partitions using the repartition method. Here we repartition the data frame into 4 partitions. Repartitioning redistributes the data evenly across the specified number of partitions by shuffling the data among nodes. This step is crucial when working with large data sets as it enhances parallelism and allows the workload to be distributed more effectively across the cluster. After repartitioning, we again check the number of partitions using getNumPartitions. To verify the data distribution, we use a custom function with mapPartitions with index. This function associates each partition index with its contents, allowing us to inspect how data is distributed across partitions after repartitioning. Step 4, coalescing data. This step illustrates how to reduce the number of partitions using the coalesce method. Coalescing is more efficient than partitioning because it minimizes data movement by avoiding a full shuffle. Here we reduce the number of partitions from 4 to 2. This is particularly useful for smaller data sets or when a reduction in partitions improves performance, such as after filtering operations. As with the previous step, we verify the number of partitions and inspect the data distribution using map partitions with index. Coalescing is a great way to optimize resource use while maintaining efficiency. Step 5, final data frame and actions. Finally, we perform an action to display the contents of the coalesced data frame. The show method is used to display the data in a tabular format, confirming that the data remains intact throughout the partitioning and coalescing operations. 2. Caching and persistence. Caching and persistence are powerful techniques in PySpark for optimizing job execution and reducing computation overhead. When processing large-scale data, certain datasets or intermediate results are often reused across multiple transformations or actions. Without caching, Spark would recompute these datasets every time they are accessed, leading to increased execution time. By caching data, we can store these frequently accessed datasets in memory, enabling faster retrieval and significantly improving performance. PySpark provides two main methods for caching: cache and persist. The cache method is a shorthand for persist with the default storage level, which is memory underscore and underscore disk. This level stores the data in memory if there's sufficient space, otherwise it spills the data to disk. For datasets that can fit entirely in memory, memory underscore only is an excellent option as it avoids disk I/O, making operations faster. However, if the dataset exceeds memory capacity, memory underscore and underscore disk ensures that the job can still run by storing the excess data on disk. The choice of caching level depends on the size of the dataset and the available resources. For example, if you are working with a dataset that is frequently used in iterative computations such as machine learning algorithms or graph processing, catching it in memory reduces the need for a computation and speeds up subsequent operations. On the other hand, if you are dealing with very large datasets, spilling to disk using memory underscore and underscore disk ensures the application stability without memory overflow errors. In summary, caching and persistence are essential tools for improving the efficiency of Spark jobs. By strategically storing intermediate results, you can reduce recomputation, save execution time, and optimize resource utilization, making them indispensable for handling large-scale data processing in PySpark. Practical example. This example demonstrates the use of caching and persistence in PySpark to optimize performance during data processing. Both techniques help store intermediate results, reducing the computation and improving the execution time for frequently accessed data. Let's walk through the code step by step. Step 1, initialize Spark session. We begin by creating a Spark session, which is the entry point for interacting with PySpark. The appName method assigns a name to this application, caching persistence sample. The getOrCreate method either initializes a new Spark session or retrieves an existing one. This Spark session enables us to create data frames and execute distributed computations. Step 2, create a sample data frame. A small dataset is created as a list of tuples, where each tuple contains information about an employee, including their name, department, age, and salary. Using create a data frame, this dataset is converted into a structured data frame with column names named department, age, and salary. This data frame serves as the input for demonstrating caching and persistence techniques. Step 3, persist the data frame. The persist method is used to store the data frame with the default storage level, memory underscore and underscore disk. This means the data frame is cached in memory. If there's enough space, otherwise it spills to disk. Persistence ensures that this data frame does not need to be recomputed for subsequent actions, saving execution time. We perform multiple actions on the persisted data frame. Count records. The count action calculates the number of records in the data frame. Filter records. The filter transformation selects employees from the HR department, followed by a show action to display the results. Group and aggregate. The grouping method groups records by department, and average salary computes the average salary for each department. Each of these actions benefits from the persisted data frame, avoiding redundant computations. Step 4, cache a filtered data frame. Next, we demonstrate the cache method. A filtered data frame is created by selecting records where the salary is greater than 5,000. This filtered data frame is cached in memory using the cache method. Caching is equivalent to persist with the memory underscore and underscore disk storage level by default. We perform actions on this cache data frame. Show records. The show action displays all employees with the salary greater than 5,000. Count records. The count action calculates the number of records in the casted data frame. The caching mechanism ensures that these computations are faster as the filtered results are already stored. Step 5, inspect storage levels. To understand the storage levels of both data frames, we use the storage level property. Persisted data frame. This data frame is stored with the memory underscore and underscore disk level, meaning data is stored in memory first and spilled to disk if memory is insufficient. Cached data frame. Similarly, the cached data frame also uses the memory underscore and underscore disk storage level by default. Inspecting storage levels confirms that the data frames are stored efficiently for use in subsequent operations. 3. Optimizing joins. Optimizing joins is crucial when working with large datasets in PySpark, as joins can lead to expensive data shuffling, impacting performance. To address this, PySpark offers techniques like broadcast joins and skew optimization. Broadcast joins are highly efficient when one of the datasets is small enough to fit in memory. By broadcasting the smaller dataset to all worker nodes, PySpark eliminates the need for shuffling the larger dataset, significantly reducing execution time. This method is especially useful in scenarios like joining a small lookup table with a large fact table. For skew data, where certain keys appear more frequently and cause workload imbalance, skew optimization can help. Increasing the number of shuffle partitions using spark.shuffle.partitions ensures better data distribution. Another approach is sorting the keys, which involves adding a random value to skewed keys to distribute them evenly across partitions. By using broadcast joins for small datasets and skew optimization for imbalanced data, you can make your join operations more efficient and scalable, ensuring better performance for large scale data processing. Practical example. The, this example demonstrates two critical techniques for optimizing join operations in PySpark: broadcast join optimization and skew optimization using sorting. These techniques are designed to handle challenges like large scale data shuffling and skewed data distributions, which are common in big data processing. Step 1, initialize Spark session. We begin by initializing a Spark session, the entry point for all PySpark operations. This provides the environment for creating data frames and performing distributed computations. The application is named Join Optimization Sample for identification. Step 2, create a large data set. A large data set is simulated by creating a list of tuples representing products with product underscore ID, product underscore name, and price. The dataset includes a skewed key, where the product ID 2 is repeated multiple times. This skew introduces an uneven data distribution, which can cause performance bottlenecks during join operations. To simulate a large dataset, the list is repeated 1000 times before being converted into a data frame named df underscore large. Step 3, create a small dataset. A small dataset is created as a list of tuples representing discounts for some products with columns product underscore ID and discount. This dataset is converted into a data frame named df underscore small. This smaller dataset is ideal for demonstrating a broadcast join as it can fit in memory and avoid data shuffling. Broadcast join optimization. The first optimization technique is the broadcast join, where the smaller dataset df underscore small is broadcasted to all worker nodes. This eliminates the need to shuffle the larger dataset df underscore large across the cluster, significantly improving the join's performance. The join operation is performed using the join method with broadcast applied to the smaller dataset. The result is a left outer join which includes all rows from the large dataset, even if no matching key exists in the small dataset. The show action displays a sample of 5 rows from the join data frame, demonstrating the efficiency of the broadcast join. This is skew optimization using sorting. The second optimization addresses skewed data in the large dataset. When certain keys like 2 in this example are repeated disproportionately, it leads to an imbalance in workload distribution. To mitigate this, sorting is applied to distribute the skewed keys more evenly across partitions. Sorting the large dataset, a new column, sorted underscore key, is added to the large dataset by concatenating the product underscore ID with a random integer generated using rand, creating unique keys for each record. Sorting the small dataset, a matching sorted underscore key column is added to the small dataset by appending a fixed value e.g. underscore 1 to the product underscore ID. This ensures that keys align properly during the join. A join is then performed using the sorted underscore key column, and the resulting data frame is adjusted to retain only the original columns product underscore ID, product underscore name, and discount. The show action displays a sample of 5 rows, showcasing the effectiveness of skew optimization. 4. Managing shuffle operations. Shuffle operations are a fundamental but expensive part of PySpark's distributed processing framework. They occur whenever data needs to be redistributed across partitions, such as during operations like group B join or reduce by key. Shuffling involves transferring data between nodes in a cluster, which introduces significant overhead in terms of network I/O, disk usage, and computation time. Effectively managing shuffles is critical for optimizing the performance of PySpark jobs, especially when dealing with large data sets. To minimize and optimize shuffles, it's important to understand when and why they occur. For example, a group A operation requires shuffling all records with the same key to the same partition to perform aggregation. Similarly, join operations need to align keys between two datasets, which often leads to data redistribution. These operations can become bottlenecks if not handled properly. Several techniques can help optimize shuffle operations. First, you can reduce the number of partitions during a shuffle by using the coalesce method, which avoids unnecessary data movement. Conversely, increasing partitions with repartition can help distribute data more evenly and prevent certain partitions from becoming overloaded. Another strategy is to use map side aggregations wherever possible. which reduces the amount of data shuffled by performing partial aggregations before the shuffle stage. For instance, using reduce by key instead of group by key achieves this by combining values locally within each partition before sending data across the network. Additionally, broadcast joins can eliminate the need for shuffles entirely when one of the datasets is small enough to fit in memory. Broadcasting sends a copy of the smaller dataset to all nodes, avoiding the redistribution of the larger dataset. Finally, tuning the configuration parameter spark.sql.shuffle.partitions allows you to control the number of partitions during shuffle operations, ensuring they are balanced and appropriate for the data size. By carefully managing shuffle operations and applying these optimization techniques, you can significantly improve the efficiency of your PySpark jobs, reducing execution time and resource consumption while maintaining scalability for large scale data processing. Example. This example demonstrates the optimization of shuffle operations in PySpark using the reduce by key and group by key transformations. Shuffles occur when data is redistributed across partitions, and understanding how to manage them efficiently is essential for improving the performance of PySpark applications. Let's walk through the code step by step. Step 1, initialize Spark session and Spark context. The example begins by initializing a SparkConf object to set the application name shuffle optimization example and a Spark session which serves as the interface for PySpark operations. The Spark context SE is retrieved from the Spark session to work directly with RDD's resilient distributed datasets. These RDDs are fundamental to PySpark's distributed data processing. Step 2, create an RDD with sample data. A sample dataset is created as a list of tuples, where each tuple contains a department name and a salary value. This dataset simulates data that needs to be aggregated by department. The parallelize method converts the list into an RDDD, dividing it into four partitions using the numSlices parameter. Partitioning ensures that the data is distributed across the cluster for parallel processing. Step 3, optimize shuffle partitions. By default, Spark uses 200 partitions for shuffle operations, which can be excessive for smaller datasets. To optimize this, the spark.sql.shuffle.partitions configuration is set to 4, matching the number of partitions in the initial RDD. Reducing the number of shuffle partitions minimizes overhead and improves efficiency for small datasets while maintaining the ability to scale for larger data. Using reduce by key for efficient shuffle. The reduce by key transformation is applied to calculate the total salary for each department. This operation combines values for the same key department within each partition before shuffling the aggregated results across partitions. By performing map-side aggregations, reduce by key reduces the volume of data shuffled across the cluster, making it highly efficient for large datasets. The results are collected and printed, showing the total salary for each department. For instance, HR 24900 sum of salaries for HR, Finance 19700 sum of salaries for Finance. Using group by key for comparison. To compare efficiency, the same aggregation is performed using group by key, which groups all values for the same key into a single partition before processing. This approach does not perform any map-side aggregations, resulting in significantly more data being shuffled. After grouping, A map values transformation is applied to sum the salaries within each group. While the output matches the results of reduce by key, the group by key operation is less efficient because it requires shuffling all the values across the cluster, consuming more memory and network bandwidth. This inefficiency becomes even more pronounced with larger datasets. 5. Reading and writing large files efficiently. Efficiently handling large files is a critical aspect of big data processing in PySpark. The choice of file format and techniques like partition pruning can greatly impact the performance of your Spark jobs. By optimizing how data is read and written, you can achieve faster processing times, reduce storage requirements, and improve query efficiency. First, choosing the right file format is essential. While formats like CSV, SV are simple and widely used, they are not ideal for large scale data processing due to their lack of compression and inefficient schema handling. Instead, PySpark supports advanced file formats like Parquet and Orc, which are specifically designed for big data workloads. These formats offer several advantages, including built in compression, columnar storage, and schema evolution. Parquet and Orc allow Spark to read only the required columns during query execution, significantly reducing I/O overhead and improving performance. Writing data in these formats ensures faster subsequent reads and better storage efficiency, making them the preferred choice for large data sets. Another key optimization technique is partition pruning, which is especially useful when working with partition data. Partitioning divides large datasets into smaller chunks based on specific column values, such as date, region, or department. When querying partition data, Spark can skip irrelevant partitions by applying filters, a process known as partition pruning. For example, if a dataset is partitioned by year, querying data for a specific year avoids scanning all other partitions. This selective reading of data reduces the amount of data processed, speeds up queries, and minimizes resource consumption. To enable partition pruning, ensure your queries include filter conditions that match the partition keys. By leveraging efficient file formats like Parquet or ORC and enabling partition pruning for partition data, you can optimize your Spark jobs for large scale data processing. These strategies not only improve performance but also ensure scalability, making your PySpark applications more effective for handling massive datasets. Example. This example demonstrates how to efficiently handle large datasets in PySpark using Parquet and CSV file formats with the focus on partitioning and selective reading. The example highlights the benefits of using Parquet for better performance and optimized storage compared to CSV. Step 1, Initialize Spark session. We start by initializing a Spark session, the entry point for PySpark applications. The application is named Efficient File Format Example, and the session provides the environment for creating and processing data frames. Step 2, Create sample data. A small dataset is created as a list of tuples representing employee records. Each record contains the employee's name, department, age, and country. The data is converted into a structured PySpark data frame with columns name, department, age, and country. This dataset will be used to demonstrate writing data in different formats and leveraging partitioning. Step 3, Define absolute paths. Paths for storing the output data are defined using Python's OS module. Two paths are created. Parquet underscore path for writing data in Parquet format with partitioning. CSV underscore path for writing data in CSV format for comparison. Using absolute paths ensures that the output is saved in a consistent location, making it easier to locate and manage the files. Step 4, Write data in Parquet format with partitioning. The data frame is written to the Parquet format using the write method. The partition by country option is used to partition the data by the country column. Partitioning organizes the data into subdirectories based on distinct values in the country column, such as USA, UK, and Canada. This makes it easier and faster to query specific subsets of the data. The mode override option ensures that existing files in the target directory are replaced if they already exist. Writing data in Parquet format provides several advantages. Columnar storage enables Spark to read only the required columns during queries. Compression reduces storage space compared to CSV. partitioning speeds up query performance by allowing Spark to skip irrelevant partitions. Step 5, read partition data. The partition Parquet data is read back using the read.parquet method. A filter is applied using filter call country user to select only records where the country is USA. Thanks to partition pruning, Spark scans only the USA. Partition instead of the entire dataset, significantly reducing query time and resource usage. The filtered results are displayed using show. This step demonstrates the power of partitioning combined with an efficient file format like Parquet, which enhances both read performance and scalability. Step 6, write data in CSV format. For comparison, the data frame is also written to a CSV file using the write method with the header true option to include column headers. Unlike Parquet, CSV files do not support partitioning, compression, or columnar storage, making them less efficient for large-scale data processing. While CSV is widely supported and easier to use for small datasets or sharing data between systems, it is not ideal for big data workloads due to its higher storage requirements and slower read-write performance. 6. Using window functions instead of Groupie. Window functions in PySpark are a powerful alternative to Groupie for performing aggregations over a defined window of rows. Unlike Groupie, which requires shuffling the data across partitions to group and aggregate, window functions operate on a defined subset of rows within each partition. This approach can significantly improve efficiency by reducing the need for full data shuffling in certain scenarios. A window function computes results across a range of rows related to the current row. For example, you can calculate running totals, rank rows within a group, or compute moving averages using window functions. The key advantage of window functions is their ability to perform these calculations while maintaining the granularity of the original data. In contrast, Groupie collapses data into one row per group, often requiring additional processing if you need to retain the original detail. One of the primary reasons window functions can be more efficient than Groupie is that they avoid redistributing the entire dataset across partitions for many use cases. Instead, Spark computes the window operation within each partition, minimizing network I/O and shuffle overhead. This makes them especially suited for tasks like ranking, calculating cumulative metrics, or finding lag and lead values in time series data. For instance, if you need to calculate a running total of sales for each department, using a window function allows you to do this efficiently without combining all rows into a single group. Similarly, when ranking employees by their salaries within each department, window functions provide a seamless way to compute rankings without disrupting the original data structure. By choosing window functions over grouping in scenarios where they are applicable, you can achieve better performance, maintain data granularity, and simplify your code. This makes them an essential tool for optimizing PySpark applications, particularly when dealing with large datasets and complex aggregations. Example, they, this example illustrates the use of window functions as an efficient alternative to the traditional groupie approach in PySpark. It highlights how window functions can perform aggregations while preserving the granularity of the original data, avoiding unnecessary shuffling, and enabling more advanced operations like ranking and row numbering. Step 1. Initialize Spark session. The process begins with the creation of a Spark session, which serves as the entry point for interacting with PySpark. The application is named Window Functions Example, and this session provides the environment for creating and processing data frames. Step 2. Create a data frame. A dataset is created as a list of tuples representing employee records. Each record contains the employee's name, department, and salary. This data is converted into a structured data frame with columns employee underscore name, department, and salary. The original data frame is displayed using the show method. Part 1, Aggregations using groupie. The first part demonstrates the traditional groupie approach to aggregations. The groupie department method groups employees by department, and the ag function is used to calculate max underscore salary, the maximum salary in each department using max salary. Num underscore employees, the number of employees in each department using count employee underscore name. While this method is straightforward, it groups the data into one row per department, losing the granularity of individual employee records. Additionally, Group B requires a shuffle operation which can be computationally expensive for large data sets. Part 2, Aggregations using window functions. The second part introduces window functions as an alternative to Group B. A window specification is defined using window.partition by department, which creates logical partitions of the data based on the department column. The with column method is used to add two new columns. Max underscore salary, the maximum salary in each department, calculated using max salary dot over window underscore spec. Num underscore employees, the number of employees in each department, calculated using count employee underscore name dot over window underscore spec. Unlike groupie, window functions preserve the original structure of the data frame, maintaining one row per employee while adding the aggregated values as new columns. This allows more flexibility in further transformations and analysis without collapsing the data into grouped rows. Additionally, window functions avoid shuffling for these types of aggregations, making them more efficient. Part 3, Row numbering using window functions. The final part demonstrates a more advanced use of window functions by assigning row numbers to employees within each department. The row underscore number function is used along with the window specification, extended with order by salary to order employees by salary within each department. The resulting data frame includes a new column, row underscore number, which assigns a unique rank to each employee in their respective department based on their salary. This operation highlights the versatility of window functions, enabling tasks like ranking, deduplication, and time series analysis without collapsing the original data structure or requiring a shuffle. And that wraps up our discussion on handling large scale data processing in PySpark. We've explored the power of PySpark's distributed computing, the importance of partitioning, the use of efficient file formats, and other optimization techniques that make it the go to framework for big data. If you found this video helpful, don't forget to like, share, and subscribe for more insights into PySpark, data engineering, and big data concepts. Thanks for watching, and I'll see you in the next video.